Welcome back to another explainer. Today we're jumping straight into an absolute bedrock concept of coding that gives software its real power. We're talking about loops in C programming, and specifically we're going to see how they operate in the truly fascinating world of embedded systems.
So picture this for a second. You're writing the code to blink a single LED on a circuit board. You type it out, turn on, wait a second, turn off, wait a second. Easy enough, right? But what if your project needs you to do that exact sequence 10,000 times? Are you literally going to sit there at your keyboard and copy-paste those lines over and over and over again?
10,000 times? Yeah, absolutely not. It's completely impossible to do this by hand. I mean, it would take hours. Your code file size would be absolutely massive, and trying to find a bug later, a total nightmare. And that right there is exactly why loops exist. They are essentially the CPU's ultimate superpower, designed specifically to handle massive amounts of tedious repetition with just a few elegant lines of code.
All right, here's our game plan for today. 1. Why loops exist. 2. The 3 core loops. 3. Nested and infinite loops. 4. Real-world embedded applications. And 5. Common programming mistakes. Let's get into it.
Section 1. Why loops exist.
You know, you've got to think of your microcontroller's CPU as this blazingly fast, entirely tireless worker. It never complains, it never gets bored, and it just wants to execute instructions as fast as electricity will physically allow. So, instead of doing all that manual repetition yourself, loops let you feed the CPU a tiny block of instructions and simply say, hey, go do this 1,000,000 times. It's this exact capability that makes dynamic outputs, things like smooth visual animations on a screen or constant audio processing, actually possible. The CPU handles all the heavy lifting for us.
Section 2. The 3 core loops.
Okay, let's break down the absolute workhorse of C programming, the for loop. It has a very strict, super predictable lifecycle. Step 1 is initialization. We set a starting point, right? Like setting a counter to 0. Step 2 is the condition. The CPU checks if our counter has reached our goal, say 10,000. If that's true, we move to step 3, execution. The CPU runs the actual embedded code, like turning on that LED. And finally, step 4 is the increment. We just add 1 to our counter, and the whole cycle loops right back up to the condition. It's perfectly structured, neatly self-contained, and it's your go-to tool when you know exactly how many times a task needs to repeat.
But what if you don't have a fixed number in mind? Well, that's where we expand our toolkit. First up, the while loop. This guy keeps executing as long as a specific condition remains true. Imagine an embedded temperature sensor in a smart thermostat. The code basically says, while the room temperature is below 70 degrees, keep the heater running. It just continuously reads the sensor over and over until that condition finally drops and becomes false. Then we have its sibling, the do-while loop. The really crucial difference here is that the condition is checked at the end of the loop, not the beginning. Meaning it guarantees your code runs at least one single time before it even asks whether it should repeat. This is incredibly handy for things like digital menu systems, where you obviously need to display the UI to the screen at least once before asking the user for their input.
Section 3. Nested and infinite loops. Now, what's genuinely fascinating is what happens when we reframe these abstract lines of code into physical hardware behavior. Think about a nested loop, which is simply stuffing one loop inside of another one. Picture an 8x8 LED display matrix. You'd use an outer loop to scan through the 8 rows and an inner loop to scan through the 8 columns to light up a specific pixel. But the second concept is where embedded programming gets really unique, the infinite loop. Now, in standard PC software, an infinite loop usually means your app just crashed. But in embedded C, an infinite loop, which you'll often see written as while one, is a feature. It's actually a requirement. It is the vital, never-stopping heartbeat of your device. A microcontroller doesn't have Windows or macOS to return to. Once you power it on, that CPU never stops. It just runs your main program animation or your core control logic endlessly inside that infinite loop.
Section 4. Real-world embedded applications.
Because let's be real, this is the magic that loops enable in the real world. Without them, your microcontroller is basically an expensive paperweight. Loops give us the precise LED blinking we need for status indicators. They allow for complex motor rotation. I mean, if you want a stepper motor to move smoothly, you need a loop to rapidly fire step commands in a perfect sequence. They're totally essential for sensor polling, continuously asking a sensor for crucial data every few milliseconds. And they even handle the gritty details of UART communication, taking a giant message and using a loop to shove it out over a wire bit by bit, byte by byte. Basically, every dynamic, moving thing a piece of hardware does relies on a loop humming along under the hood.
Section 5. Common Programming Mistakes.
All right, we do need to talk about the dark side for a second here. Loops demand absolute precision. If you mess up the logic, your program will completely freeze. The classic rookie error is the accidental infinite loop. Remember how we just said infinite loops are great for the main program? Well, they are disastrous if they happen by accident right in the middle of a math calculation. And this almost always comes down to a missing increment. If you forget to tell your for loop to actually add 1 to the counter, your goal is never reached, and your device just hangs. You literally have to hard reset it. Another major trap is simply writing the wrong condition, like using a less than sign when you definitely meant greater than. Because of that one tiny typo, your loop either runs 0 times or it runs endlessly.
Thankfully, C programming doesn't leave us totally stranded. We have some emergency escape hatches to control the flow when loop conditions get a little tricky: the break and continue commands. Think of break as pulling the emergency brake on a moving train. If a critical error happens inside your loop, break instantly kicks you completely out of that loop, completely bypassing any conditions. Continue, on the other hand, is a bit softer. It's like the skip button on a playlist. It stops the current iteration right in its tracks and jumps straight back to the top of the loop to evaluate the next cycle. They're incredibly useful shortcut tools for keeping your code efficient and, more importantly, safe.
So we've successfully given our CPU the ultimate superpower. We can scan matrices, control motors, and pull sensors endlessly. But this brings up a pretty massive new challenge. As our programs grow to hundreds or thousands of lines of repeating tasks, how on earth do we organize all this code so it doesn't turn into a tangled, unreadable mess? How do we take these powerful loops and package them into neat, reusable building blocks? Well, that is exactly what we're going to uncover in our next explainer when we tackle the brilliant architecture of functions. Until then, keep experimenting, and thanks for joining us.